Hello everybody, my name's Simon George and I'm presenting on behalf of the IODP Expedition 378 Science Party. And the talk is Hydrocarbons in a new early Paleocene sedimentary section recovered from the Campbell Plateau, south of New Zealand by IODP Expedition 378. First up, I'd like to acknowledge the Geordie's Resolutions ship crew, shipboard IODP staff and the science party, the whole science party of Expedition 378. I received funding from ANZIC IODP, which enables me to take part in the expedition. And I'd like to thank Kelly in the ANZIC office for multiple flight and accommodation changes. I'd also like to introduce you to by photograph the named co-authors, including Blanca, who's an organic geochemist on the expedition, Laurel, who's the staff scientist from IODP. Röhl and Debbie are the two co-chief scientists of the expedition. Chris from IGNS is a biostratigrapher, and Erica Crouch has joined us as a post-cruise participant to help us with the biostratigraphy. So arguably, Expedition 378 was somewhat ill-fated. It was originally scheduled for 2018 in the Geordie's Resolution, but there were cracks discovered in the propellers a few weeks out. So we were rescheduled to 2020. And then on the 24th of December 2019, we all get an email saying there's a derrick problem with the JR and we couldn't drill deeper than 2 kilometers. And this ruled out all these potential holes in the middle of the South Pacific. Very disappointing. But anyhow, we decided to continue and re-drill DSDP 277. And we shortened the expedition from 8 weeks to 4 weeks. We started in Fiji, transited down, did the drilling, and then back to Tahiti. So we scheduled from the 3rd of January to the 6th of February 2020. And we came back to shore with loads of sedimentary rocks, data, and new collaboration plans. So it was a great success. We just avoided COVID-19, and in retrospect, we see that we were one of the few ocean drilling expeditions with a full shipboard science complement that were able to complete an expedition in 2020. So somewhat good fate in the end. So why DSDP 277 redrill? Well, it sits here on the Campbell Plateau, just south of Auckland Island. It's a classic hole drilled in 1973 in about 1,200 meters water depth. And it's classic because it has a high latitude paleoclimate record. The oxygen isotope curves that define the unusually warm early Eocene period were first derived from sediment from here. It's a single, partially cored hole though, and the core recovery below the Oligocene was quite patchy, so big gaps. And very importantly, it's rather poorly preserved now, like many of us age more than 45 years. So Expedition 378 had some great outcomes. We drilled 5 holes at the location, including A, B, and E, which are APC and XCB holes, and holes C and D, which are the deeper rotary core barrel. We were on site 11 days. We got 912 meters of core, including the first continuously cored multiple hole Paleogene sedimentary section from the Southern Campbell Plateau. You can read about this in the preliminary report from which this table is taken. Here's a lithological summary of U1553. We have the 5 holes shown to the left, A, B, C, D, and E. We have 5 lithological units. Lithological unit 1, 2, 3, mainly Eocene, 4, the transition Eocene to Paleocene, and unit 5 in the early Paleocene. This diagram shows a microfossil summary. And I put this in not so much to show you the microfossils, but to point out that we are bracketing a very important period in Earth history. And we haven't done the core sampling yet because of COVID restrictions in the USA, but when we do the detailed analyses, we'll likely find that we've got excellent recovery of the Eocene Oligocene transition, the EOT, the Middle Eocene Climatic Optimum, MECO, other Eocene Thermal Maximum events, and importantly, the Paleocene Eocene Thermal Maxima, the PETM down here. We got excellent recovery from the PETM in 2 cores, including both the lead into the hypothermal and the exit from it. And it was pretty exciting on board the ship when these came on board, and even the ship's captain came down to see these rocks. This diagram shows that we got much better core recovery at 1553 than DSDP 277. Reflects a better core technology nowadays. We got deeper than 277, and we discovered a new Paleocene siliciclastic unit that had never been drilled before, Unit 5. And that's the subject of this talk. The base of the unit was not drilled, so we didn't get down to the Cretaceous. So Unit 5A is early Paleocene, and it's got a carbonate-rich sandstone at the top, underlying limestone, followed by mudstone to dolomitic mudstone, occasionally sandy. There's beautiful trace fossils and concretions. And then Unit 5B is a bit deeper, mudstone to dolomitic mudstone, occasionally sandy, strong dolomitization. See these lovely dolomite rhombs, and lots of concretion still, and some beautiful trace fossils, and moderate to heavy biotubation. Unit 5B was quite gassy at the base, and eventually, in fact, that stopped us drilling deeper. There was a distinct oily smell from the core when the core was brought on the core deck and was cut, and there was fluorescence from the core surfaces under UV light. So I sampled some of these core surfaces in order to get some of the oily material into the organic geochemistry lab as quickly as possible. In terms of the onboard data, we did gas analyses, and these showed negligible hydrocarbon concentrations shallower than 480. But going from Unit 4 to Unit 5, there was a sudden increase in the methane concentrations. And as well as methane, we had ethane, propane, butane. So the wet gases in general increased quite significantly at the base of the hole. And this correlates with the position of a low porosity period in this hole. And possibly this was acting as a physical barrier for upward gas migration. The high gases could be either in situ methane production, possibly by microbial activity, which certainly could be happening, but also potentially upward migration of thermogenic gas. So what does the organic geochemistry of these hull oils from these core surfaces show? Well, we've done GCMS, gas chromatography, mass spectrometry, and this is a MZ85 mass chromatogram from that GCMS. Molecular weight from left to right increases with retention time, and these numbers show the different alkanes. It's a bimodal distribution, highs at C14 and at C20. So this is consistent with a dual source that's been extracted from this core surface. This shows MZ57 chromatograms showing low molecular weight methyl alkanes, including methyl tetradecanes and methyl pentadecanes. And these are consistent with oil window thermal maturity in these low ends. The hopanes we analyze using a technique called MRM, and these partial chromatograms from C27 to C31 show the distribution of the hopanes in the sample. And I've colored some of the isomers orange. These are the beta-beta ones, which are only found in fairly immature rocks. So this is consistent with a low thermal maturity. Similarly, the steranes, MZ217, also significant amounts of the beta-alpha alphas, an immature biomarker, and the 27s are more dominant than 29s. So together, this is consistent with low thermal maturity and a dominantly marine organic matter input. Many aromatics, including these trimethylnaphthalenes in the MZ170, and calculated reflectance from the trimethylnaphthalenes and the methylphenanthranes indicates about 0.78 reflectance. This is an oil window thermal maturity. So in terms of the summary, we have a mixed signal in the early Paleocene. We have thermally mature migrated hydrocarbons associated with gas, possibly from the Cretaceous, and indigenous immature hydrocarbons from the Paleocene rock matrix. Many thanks for your attention.